Yeah, let me recapitulate whatever that I did in my last class. In one of the configurations of half controlled bridge, we found that as alpha tends to pi, the incoming thyristor fails to turn on, and therefore the outgoing thyristor fails to turn off. Okay. As a result, the output voltage waveform, if I see, from 0 to pi we have a freewheeling period, and from pi to 2 pi output voltage is same as the input voltage. Okay. So there is source supplies power only in one of the half cycles, and in the remaining half a cycle there is a complete freewheeling part, provided the load current is continuous. Okay. So output voltage is same as that of a half wave rectifier. In the very first lecture on converters, if you see the waveform, they are both the same. Hence the name half waving effect. Okay. Then second point what we discussed was the expression for the average value of the output voltage is given by Vm by pi into 1 plus cos alpha. Remember, this expression is valid only if the load current is continuous. Remember, load current should be continuous, only then this expression is valid, because we got this expression by integrating the output voltage. The output voltage is Vm sin omega t from pi to alpha to pi, and pi to pi plus alpha it is 0, is a freewheeling period, and from pi plus alpha to 2 pi again it is Vm sin omega t. So only when you integrate this waveform you will get the average value is Vm by pi into 1 plus cos alpha. So only if the current is continuous, this is the output voltage is given by V naught Vm by pi into 1 plus cos alpha. Remember, invariably students make a mistake while solving a problem. The moment they see half control bridge, they immediately automatically they write average value of the output voltage is Vm by pi into 1 plus cos alpha, even though the current is discontinuous. Don't make this mistake, please. Yeah, now all this time we are discussing about controlled rectification. So I have a question to ask: why do we require the variable voltage DC supply? Why do you require variable voltage DC supply? Now let me take a diversion, in the sense I'll go back to machines. In my introductory lecture I told you that in power electronics, to appreciate power electronics you need to have a really good background, a good knowledge of machines. Little bit of everything is there in power electronics, remember. So to appreciate power electronics, a reasonably good knowledge of machines is essential. Okay, let me review DC machines. Okay, a separately excited DC machine. Okay, very popular equation, V in is equal to EB is the back EMF plus IARA. V in is equal to EB plus IARA. EB is the back EMF which is proportional to flux and speed. This flux is proportional to the field current, so therefore EB is given by K into IF into omega. Therefore omega is given by V in, the input voltage to the armature. Input voltage to the armature is not the input voltage to the motor or something like that. In a sense, if I connect a resistor in series, so that is not V in. Okay, V in is the voltage applied to the armature terminals AA. Remember, okay, V in divided by K into IF minus IARA divided by KIF. Your teacher who taught machines, he might have told you that for all the practical purposes, a separately excited DC machine is a constant speed machine. In other words, the reduction in speed with load is not much. This term is generally small, because armature resistance, which comes in the path of the main power flow, should be very small. If Ra is high, I squared R losses are high, efficiency comes down. So armature resistance should be as small as possible. Moreover, armature reaction, what it does, it tries to reduce the air gap flux, so therefore armature reaction tries to keep the speed of the motor almost constant. Okay. So therefore, for all practical purposes, separately excited DC machine is a constant speed motor. Application requires a variation in speed over a wide range. What should I do? I have to change the no load speed. This term is independent of the armature current. So I have to change the no load speed. So we found that omega, the no load speed, is proportional to the input voltage to the armature Vn, and inversely proportional to the flux or If. So if I have to decrease the speed below the rated, I will apply a reduced voltage to the armature. So speed is directly proportional to the input voltage to the armature. Okay. So for any speed from 0 to the rated, Vin should vary from 0 to the rated voltage of the machine, and I will keep the flux constant. Okay. If I want to increase the speed above the base or above the rated, I will keep voltage applied to the armature at its rated value, because a good engineering practice is one should not apply a voltage higher than the rated to the motor. A general engineering practice, a good engineering practice. So I will try to reduce the field flux. So my speed, no load speed, increases. Okay. So therefore, from 0 to base speed, applied voltage to the armature terminals should be varied, and from the speed above the base, decrease the field flux or decrease the field current. So both these regions, or if I have to vary the applied voltage to the armature, or if I have to vary If, I need to have a variable DC supply. Now you may say that I will connect a rheostat in series. That's what we do in our machines lab. It's basically a highly inefficient way of handling power. Please, having done a course on power electronics, don't use a resistor in series of any circuit. It's a crime. Please, having done a course on power electronics, your solution should not contain the use of a resistor that comes in the main path of the power flow. Just not accepted. Okay. So that's what I said. One of the ways, maybe our teacher, machine teacher, the one who taught machines, might have told that connect a resistor in series with armature and connect a resistor in series with the field, vary them to vary the speed. That's fine in course 1, or that's fine in machines course. Definitely this solution is not acceptable once you do a course on power electronics. Okay. So coming to power electronics again, so both of them require a variable voltage DC power supply. Okay, so I can have a semi-controlled or half controlled bridge here. I can have a let's see, as the power rating increases, what modification do I need to make in the power circuit. Okay, one of the options is I can have, in both the cases, I can have a semi-controlled bridge. You may say, why not use a half wave controlled rectification using one thyristor? What did you found yesterday? I solved one problem, a very good problem. The moment I use only one thyristor between the source and the load, or in other words, in half wave controlled rectification, we are drawing a DC current from the source. In other words, average value of the current drawn from the source is finite. Source does not supply any power beyond pi if I use a freewheeling diode. You have observed that. Okay, so there is a DC component coming from the source, okay, plus the harmonics. Harmonics are there in both the cases. Whereas in this case, if I use a semi-controlled or half-controlled bridge, DC component is 0. There is a pulse or source supplies power from alpha to pi in the positive half and pi plus alpha to 2 pi in the negative half. So average value of the source current is 0. So DC component is 0. So half wave rectification could be a solution for a small motor, a fractional HP DC motor. Use of half wave rectification may be justified because small HP motor cost is very low. So my controller also, the so-called the power processing equipment, should also be very low. I can't have a very expensive equipment to vary the speed of a small motor. Okay, so varying the speed of a small motor, half wave rectification could be a solution. Okay, because current that I am drawing from the DC, the average value of the current that I am drawing from the source is a very small. Okay, I told you yesterday that I will solve a very interesting problem. Yeah, see, a very interesting problem. Lot of things are there. Try to understand. It's not very simple. Not very simple. It looks very simple. My sincere request to you is don't go by looks invariably. You will get cheated. So if the circuit is very simple, it may be the performance may not be as simple as that. Remember, I have a simple transformer. Input winding primary is connected to the source, secondary is connected to, or secondary is supplying a resistive load through a diode. The moment I connect a diode in the circuit is no longer linear. Remember, linear in the sense the circuit doesn't or in other words, the law of superposition doesn't hold good for this circuit. Circuit is non-linear. Input voltage is sinusoidal. Therefore, there is a very small winding resistance and maybe a very small leakage flux also. So, if V1 is sinusoidal, I can safely assume that E1 is also sinusoidal. Okay, since winding resistance and leakage flux are very small, I can safely assume that V1 and E1 are sinusoidal. V2 is also sinusoidal. Okay, output voltage across R is a half wave rectified waveform. Half wave rectified. The secondary voltage, output voltage across R. Load is purely resistive. Current waveform is also half wave rectified. So current flows in the load, remember current flows in the load from 0 to pi, okay. The expression is given by secondary sinusoidal voltage divided by R, that is if I say some x into sin omega t, so expression for I is x into sin omega t divided by R, and from pi to 2 pi current is 0, current is 0. So in other words, secondary does not supply any power to the load from pi to 2 pi. So if I write the Fourier series or Fourier spectrum for the current, it has a DC component. I discussed yesterday, it has average value is finite. So it has a DC component. Then I have a fundamental component x sin omega t, or the frequency of the first term is same as that of the input, and it has a higher omega terms, okay. Now question is, how does the source current look like? How does the source current look like? What are the principles? What are the our mission teacher, he has told us one thing, that is, in a transformer, for the AC components there has to be a ampere turn balance. If there is a AC current flowing in the secondary, there has to be a equivalent AC current in the primary, neglecting the magnetizing current. Ampere turns N1 I1 should be equal to N2 I2. Magnetizing current is neglected. Secondary current has a sinusoidal component, has a DC component. I will repeat, the secondary current has a DC component. The flux in the core has a sinusoidal component which is produced by the magnetizing current, which induces a sinusoidal voltage in the primary as well as in the secondary, and it can have a DC component, because the DC component in the core does not induce any voltage even in the primary or secondary. I cannot have a DC component in E1 or the secondary voltage E2. In other words, there you cannot have a DC component either in E1 or E2. To have a DC component, why am I saying this? To have a DC component in E1 or E2, flux is a ramp, because E is d phi by dt. To have a constant E, phi should be a ramp. So in other words, if flux is a ramp, then there is no steady state. Is that okay? So remember, the flux in the core has a DC component which does not induce any voltage in the primary as well as in the secondary. You cannot have a DC component either in E1 or E2. Why am I saying that? To have a DC component in E1 or E2, flux should be a ramp, should vary with t. So if flux varies with t, only then d phi by dt is a constant. Since flux is varying with t, so there is no steady state. So we have to eliminate that. The magnetizing, the sinusoidal flux produced by the magnetizing current drawn from the source is sinusoidal. For every high frequency component which is there in the secondary, an equivalent current should be there in the primary. Remember, for every high frequency sinusoidal component which is present in the secondary current, there should be an equivalent high frequency current in the primary. Okay. You cannot have a DC current in the primary. Why am I saying this? Assume that there is a DC component, okay, or if there is a DC component, see there is a small resistance, winding resistance here. See, I will model it. Input voltage, a small winding resistance, and E1. Okay. I said V1 is sinusoidal. I said E1 cannot have a DC component, remember. So if I apply KVL, it fails, because if as a DC component, if I average is finite, the DC component into R, average DC voltage is required here. There is a voltage drop across R, which is a DC. Input is AC, which is sinusoidal. Induced voltage is also sinusoidal. So KCL fails. So you cannot, any circuit cannot violate the physical laws, whether it's a power electronics or any subject cannot violate the basic laws, remember. Okay. So far if you see the entire, in my course I have used KVL and maybe maximum first order differential equation, R, L and E, and input is sinusoidal, only this much, nothing else. So KVL has to hold good. So I will repeat, if there is a DC component in the source, I told you that winding has a small resistance, I into R is going to be a DC voltage, input voltage is sinusoidal, induced EMF is again sinusoidal, you cannot have a DC component there. So KCL fails. Therefore, your input current has no DC component, it has all the components of AC component of current which is there in the secondary, the equivalent, and the fundamental component. So how does the primary current look like? Secondary current, the primary current should not have a DC component, rest all the components should be there in the primary. So primary current looks like this. It's like, I do not know how many of you have seen the oscilloscope, waveform in the oscilloscope. If I keep a waveform which is having a DC bias, and keep it in AC mode, how does it look like? The DC bias goes. I get a waveform symmetrical along x-axis. If I keep in DC mode, automatically I get a DC bias. You go back and check if you not observed a waveform on the oscilloscope having a DC bias. You give a sinusoid using a signal generator, give a DC bias, keep it in AC mode. The moment you keep it in AC mode, the DC bias disappears, vanishes, you get a waveform symmetrical about the x-axis, and if you keep it in DC mode, whatever the waveform with the DC bias will come on the screen. So same here, this waveform actually is the waveform which you can see in the oscilloscope with the DC bias. So remove the DC bias, I will get this waveform. So source current looks like this. Okay. Source does not supply a DC component, but then I told you that flux in the core can have a DC component. So what? So flux in the core has a DC component, phi DC, and a sinusoidal component. This flux is produced by the magnetizing current. So flux in the core is phi DC plus phi fundamental. So I have a waveform, a sinusoidal waveform having a DC shift or DC bias. What is the effect? What is the consequence? What will happen if there is a flux or DC flux in the core? Again, our machine teacher might have told us that, or told you that. Of course, the same machine teacher who taught me has also told me that invariably we operate the machines or any magnetic circuit at the knee point. A knee point is the point wherein the saturation just begins to start. So all the magnetic circuits, when I apply the rated voltage, it produces a rated flux, okay, rated AC flux. I am talking about AC now, AC flux. So the operating point is the knee point, it is assumed. But then in this case, because of half-wave rectification, there is a DC flux. So my excitation has increased in one cycle, or in one cycle there is an increase and in another cycle there is a decrease. So what will happen to the BH loop if I see I have a non-symmetrical BH loop? As the value of DC flux increases, I may have a flux in the core, or the value of the DC flux may be equal to the peak value of this flux. So it may so happen that it may not even come down to negative, and it may so happen that in that case flux or core may saturate. Core may saturate. What happens if the core saturates? We have been told that if the core saturates, core loss, your current is going to be peaky. Current is going to be peaky, and the moment current becomes peaky, the harmonics or not. The effect of harmonics again I will discuss sometime later. So therefore, if there is a DC flux in the core, in some part of the cycle, core may get saturated, and if the core saturates, a source current drawn from the source may become peaky, and the moment it becomes peaky, it's not a sinusoidal now, no longer a sinusoidal. Source current becomes peaky, has harmonics, and the effect of harmonics we will discuss sometime later. Of course, core saturation, core loss also will increase, core heating, what not. Okay. So this is the problem with half wave rectification. We are drawing a DC component. If this DC component flows in the transformer core may get saturated, core loss, current becoming peaky, and harmonics. So that is the reason half wave rectification is only used for low power application. When I am saying low power, current drawn from the source is also very small, so the effect of saturation is not much. High power, you cannot use half wave rectification. So I hope all of you understood the effect of drawing a DC current from the source. Magnetics may get saturated, bottom line. Okay. Yeah, let me solve another problem. A half controlled bridge, two thyristors in one leg, load is RE. The moment I am saying when its load is RE, first thing that should come to your mind is load current is discontinuous. Okay, first thing that should come to mind is RE is load is invariably discontinuous. The problem says determine the average value of load current for alpha is equal to 0. Nothing has been said whether the current is discontinuous or current is continuous. By looking at the circuit, you should be able to tell that current is discontinuous. Like a doctor, when he sees a face of a patient, he can understand whether the patient is having any illness or not. That's the way when you are having done half controlled bridge or so far having done a course on power electronics, the moment I see the circuit, I should be able to tell, or I should make a wild guess that whether the current is continuous or not. Here I don't need to, or no, you don't need to mention that current is discontinuous. By seeing the circuit, input is sinusoidal, output is R and E. E always opposes. R voltage across the R and current flowing are in phase. So current is discontinuous. Okay. See the waveform. We have a sinusoid. This is E. Okay. So SCR gets forward biased only when instantaneous value of the input voltage is higher than 100 volts. Again, I am neglecting the device drop. It has been mentioned that neglect the device drop. If I consider device drop, invariably we consider 2 volts for thyristor, maybe 1.5 volts for a diode, again depends on the current rating. Instantaneous value of the input voltage should be slightly higher than 100. So, okay. So having said that, thyristor gets forward biased only at 0.1 pi, or sin inverse 100 divided by 230 into root 2 is 18 degrees is 0.1 pi. So beyond 0.1 pi, if you want, you can trigger and thyristor starts conducting. But in the problem it is mentioned that thyristor is triggered at 60 degrees. So 0 to 60 degrees, no current is flowing in the load. So to draw the load voltage waveform, remember I might have told you many times that you need to know the type of load. If the current is continuous, you don't need to know the type of load, because the load voltage is either the input voltage when the thyristor in the powering mode, when the source supplies power to the load voltage is same as the input voltage, and in the freewheeling mode load voltage is 0. So you have either the input voltage or 0. Okay. Whereas if the load current is discontinuous, you need to know the type of load. Okay. Here is RE, so load voltage is E, the magnitude of E. So 0 to 60 degrees, output voltage is 100 volts. At 60 degrees, you have triggered the bridge. So T1 and D2 starts conducting in the positive half. The equivalent circuit is T1, load, D2, back to source. So input voltage is same as the output voltage, or output voltage is same as the input voltage if I neglect the device drops, otherwise it is less by a very small value, maybe of the order of 4 to 5 volts. So input is 230 minus 4 doesn't matter, still 230 for an engineer. Okay. Where does it stop conducting? Load is RE. I did tell you that the difference Vi minus E is across R. So voltage across R is nothing but I into R. Okay. So V minus E is 0. So therefore I should be 0. So at pi minus alpha min, this is the instant wherein E is equal to the input voltage Vi, current becomes 0. So current becomes 0 at 0.91 pi. Okay. I repeat, you could have triggered the thyristor at 0.1. If I had diode here, D1 and D4 instead of T1 and T4, D1 would have started conducting at 0.1 pi and would have stopped conducting at 0.9 pi because they get forward bias at that instant. We have here thyristors and they are triggered at 60 degrees. It is forward bias, it starts conducting, but then at 0.9 pi instantaneous value of the input voltage is same as the value of E. So Vi minus E is 0. So Vi minus E is nothing but I into R. So I has to be 0. So current becomes 0 at 0.9 pi. So thyristor turn off, thyristor T1 and D2 turn off at 0.9 pi, and from 0.9 pi till you trigger the next pair, that's only at pi plus alpha, that is at 240 degrees, current flowing in the load is 0. No current flows, no current flows. So load voltages is the value of E. So that's why be careful, please. Off control bridge, alpha is 60 degrees. Mechanically don't write Vm by pi into 1 plus cos alpha. Invariably you will make this mistake. Remember, don't ever do this. First you find out, first you draw the voltage waveform V0 and then you find out the average value. You can make a mistake while integrating. I told you this is a course on power electronics. You cannot make a mistake while drawing the output voltage waveform. You can make a mistake while simplifying, maybe I may not deduct, as a teacher I may not deduct any marks, but then if you make a mistake while drawing the waveforms, definitely I will deduct marks. Okay, it just gives me a feeling that you have not understood power electronics. Okay, so output voltage is from 0 to pi by 3, it is E. From pi by 3 to 0.9 pi, it is Vi sin omega t. Input voltage is same as the output voltage, and from 0.9 pi till you trigger, that is at 240 degrees, it is E. Yeah. Now why there is a jump here from E to straight away this value? Why there is a jump? It is E all of a sudden. It's because just prior to 60 degrees, what is the output voltage? It is E. If I neglect the turn on time of the devices at just immediately after 60 degrees, what is the output voltage? Is same as the input voltage, that is 230 into root 2 into sine 60 or sine pi by 3. Okay, so just before 60 degrees, it is E or 100 volts. Immediately after 60 degrees, it is 230 into root 2 into sine 60. Okay, so the output voltage instantaneously jumps from E to the instantaneous value of the input voltage at omega t is equal to alpha. So there is a jump. So this is why there is a jump here. Again, I am neglecting the device, the turn on time here. Okay, so this is the jump. So we need to find out the average value of this waveform. So if I know the average value of this waveform, that is equal to I average into R plus E. KVL has to hold good, isn't it? Okay. So average value is 0 to pi by 3 is e d omega t dt plus pi by 3 to 0.9 pi Vm sin omega t plus 0.9 pi to pi, it is e dt. Is found to be 193.45 volts. Please do not get bogged down with this value. So if the waveform is right, any 11th standard boy can write this equation and he can solve. I have not, in the sense I did solve this, but then it could be, okay, it is 193.45. Even if it is wrong, don't say that sir it is wrong, doesn't matter. As long as you understood the subject, as long as you have drawn the waveform, fair enough, more than enough. So average value of I, now I average divided is equal to V average, average value of the output voltage minus E divided by R. So 193.45 is the average value of the output voltage, sorry, average value of the output voltage, not average line, average value of the output voltage, sorry about that, minus 100 divided by 10 is 9.435 amps. Okay. What the part B says, what is the new value of the average current flowing through the load if a large L is connected in series with the load? The moment the problem says that a large value of inductor is connected in series, the first thing that should come to your mind is current is continuous. Okay? You don't need to mention that current is, specifically you don't need to mention that current is continuous. You just want to tell that a large inductor is connected in series with the load. So first thing that comes to my mind is current is continuous. If the current is continuous, life is very simple, man, in the sense I just need to know the value of alpha. From alpha to omega t is equal to pi is output voltage is Vm sin omega t, and from pi to pi plus alpha output voltage is 0, and again is Vm sin omega t. Okay. So I have not drawn the output voltage waveform. It is same as the waveform which we have drawn for case 1 or case 2. 0 to alpha output voltage is 0, alpha to pi it is Vm sin omega t, and from pi to pi plus alpha again 0, and from pi plus alpha to 2 pi it is Vm sin omega t. So average value is Vm by pi into 1 plus cos alpha, so 155 volts. So average value of I is same as average value of the output voltage minus E divided by R, that is the current. Okay. I will solve yet another problem. Off control bridge, RE load. Life is a bit difficult when it becomes just a RE load. Life is very simple when the current is continuous. Trigger angle is maintained at alpha is equal to 110 degrees. Current becomes 0 at 50 degrees beyond the zero crossing. So I will repeat, say current becomes 0 at 50 degrees beyond the zero crossing. Sketch the load current and applied voltage waveform. Okay. And also determine the value of E. E is not known. E is not known. Okay. Again, same, where does one trigger the SCR, or if I apply a gate pulse, from where onwards it will start triggering. Okay. Alpha min should be equal to sin inverse E divided by Vm. Okay. E is not known. Definitely it should be less than which value? Less than? E should be definitely less than 90 degrees. If it is, sorry, alpha min should be less than 90 degrees. I can't have alpha min greater than 90. If that alpha min is greater than 90, it implies that what does it imply? Maximum value of sine inverse. It implies that value of E is same as the peak value of V in. So there is no current at all, you can't trigger the thyristor at all, okay, you can't trigger the thyristor at all. Thyristor is triggered at 110 degrees. The problem says that current becomes 0 beyond 50 degrees, in the sense you have triggered at 110, current starts flowing and it becomes 0 beyond 50 degrees beyond this point. So at steady state, or maybe at the end of the first cycle, maybe current becomes 0 at 230 degrees, current becomes 0 at 230 degrees, or pi plus 5 by 18 pi, this is the load current. So similar waveform will be there. So it starts at 11 by 18, that's 110 degrees, increases and becomes 0 at 5 by 18 degrees. But how does the output voltage waveform look like? From 110 to 180, 110 to 180 degrees, Vi is equal to V naught, or V naught output voltage is same as the input voltage. So in a discontinuous mode, remember, in discontinuous mode, as long as the thyristor conduct, input voltage is equal to output voltage in the positive half. I mean, it may so happen that I told you that current may become, if the current were to become 0 before pi, okay, from 110 to the instant where the current becomes 0, the load voltage is Vi. Fortunately here current becomes 0 beyond pi. So the load voltage is V naught is same as Vi from 110 to pi. 110 degrees to pi, it is Vm sin omega t. From pi to 230 degrees, or pi plus 5 by 18 pi, freewheeling diodes are conducting now, freewheeling diodes are conducting. Output voltage is 0 theoretically, otherwise you may have around maybe 3 volts or so, 0. At 230 degrees, current dies down, no current is flowing now, VO is same as E. Okay, if I have RL load, output voltage is also 0. So but here we have a RE load. So at 230 degrees current becomes 0, from 230 to 290, that is 180 plus 110, or till you trigger the thyristor, next pair of thyristor, that is next thyristor here, T4, output voltage is same as E. Okay. So if you see here, current starts increasing from 110 degrees because you have triggered the thyristor, current starts increasing, becomes 0 at 230 degrees, load current. So from alpha to pi, source supplies power T1, D3, because current is flowing at that time, output voltage is same as Vi, 0 from pi to 5 by 18 by, that is 230 degrees, freewheeling diodes are conducting, here, T2, T1 turns off because we have a common cathode configuration out of which one of them is the diode. So the moment B potential becomes higher than A, D3 starts conducting, So which turns off T1, that half waving effect is not there here irrespective of alpha, because immediately in the negative of omega t is equal to pi plus D3 starts conducting, this turns off, which is not the case if I replace D3 by a thyristor there and T4 by a diode. If I interchange these two, then we may have a half waving effect, I told you, because T1 continues to conduct till T3 is triggered, okay. Just to remind you, nothing to do with this problem maybe, okay. So this is the waveform. So from pi plus 5 by 18 pi to pi plus 11 by 18 pi it is E, then again Vm sin omega t. So I need to find out the average value of this waveform. See, how does the source current look like? Source current is same as the load current in the powering mode. When is the powering mode? When T1 and D2 are conducting, it is a powering mode because source comes in series with the load, and similarly in the negative of when D3 and T4 are conducting, source comes in series with the load, so that is the powering mode. So source current is same as the load current. At omega t is equal to pi plus T1 turns off, I have assumed source inductance to be 0, okay. So immediately T1 turns off, so there is a step jump from immediately current becomes 0, source current becomes 0, instantaneous. This is almost instantaneous because source inductance is 0. Immediately turns off, but then the difference between the load current, now the load current starts flowing through D2 and D3. Same thing happens in the negative off. So the problem is very simple. I need to know I need to find out the average value. It is given by this equation, 1 over pi from 110, in the sense 110 degrees to pi, it is Vm sin omega t. From pi to 230 degrees, freewheeling period, d omega t, 0 d omega by dt. From end of the freewheeling mode to till you trigger the next pair, that is pi plus 110 degrees, it is E d omega by dt. So this is one complete, this is half a cycle. So you substitute the value for Vm is 230 into root 2, integrate it. So this is the average value. I got an average value in terms of E. Now I average is V average minus C divided by R. So value of I average is 1.8 amperes, R is 6 ohms, it is given, these are the two parameters are given. So E is 85.9 volts. Again a very educative problem it is, since almost all the concepts that which I emphasize, they are there. Again I did not blindly use the output voltage, average value of the output voltage is Vm by pi into 1 plus cos alpha, alpha is 110 degrees. No, I did not use that. So RE load, discontinuous, I drew the waveform, then I found out the average value and determined the current. So remember the important concepts, that expression is valid only if the current is continuous, otherwise it is not. The moment you get a problem, think for a while, spend some time with the problem, think for a while, draw the waveform. If you draw the waveform, I am telling you 90% of the problem is done, you are through, I am telling you. Okay, thank you.